Good afternoon, everyone, and welcome to our webinar. Yeah, very pleased that you could make it. And I just wanted to give a brief introduction to myself and my company. I am John Knott, and my company is JD Technologies Global, and we're a field sales company that represents manufacturers. So another term for our firm is a representative or an agency, and we're pleased to set up this webinar to give you a little bit of history. We were going to do a series of webinars as a celebration of our 20th year anniversary, and we had such a great response that we decided we're going to be doing this throughout the year, and this will be our first one ending 2025, and then we're going to start having one, probably one a month, starting in January. Technical, these aren't sales pitches, they're very technical. So we're again pleased that you're here. One thing I'd like to mention is that we are certified. We have a certification. Everybody knows about AS 9100 and ISO 2000, all the certifications that companies get in their respective industry. A lot of people don't realize that rep firms get certified, and so we are a certified manufacturer's rep. Before we get started, a couple of housekeeping notes. Questions and answers. We welcome questions and answers. What we're going to do is we're going to have the questions and answers at the end. If you have something that you really want to have an answer, raise your hand or put an answer in the queue, put a question in the Q&A, and we'll get it answered. But for the most part, we're going to wait to the end, and we're going to have an open session, and you're going to raise your hand. And whoever raises their hand, I'm going to open up your mic so you can see it. The other thing I wanted to mention is you are going to get a copy of Bud's presentation, and you're also going to get a copy of this webinar. So you don't, in the form of a video, so you don't have to be taking notes or taking screenshots. You're going to be getting everything that you see. So I'd like to introduce Dr. Harold Vincent, goes by the name of Bud, and he's a former research professor, retired naval officer, and small business entrepreneur. A lot of experience in the area of ocean systems in general and underwater acoustics in specifics. That includes communication, signal processing, electronics, systems engineering. If you're in the wrong webinar, you can leave now, but we're very lucky to have him here. Welcome, Bud.
So we're going to talk today about underwater acoustics, with some focus on navigation and communication, and how the other domains of ground, sky, and space relate to maritime and undersea operations. Won't talk as much about ground, more so the in-air and space aspect and how it ties to undersea. So the overview of today's presentation, I'm going to give a little further overview of my background beyond what John just provided. Quick company snapshot of DBV technology, and then the meat of the technical discussion. We're going to talk about undersea vehicle navigation. And before we get into that, we're going to go over some terminology. And I apologize in advance. There's a lot of acronym soup involved in this this area. We'll talk a little bit about techniques, and then underwater acoustic positioning and communication, and then go into a couple examples of where the undersea navigation and communications and this bridge to air and space takes place. And that'll be an undersea tracking range, the use of an AUV in a deep seafloor survey, a scientific area called seafloor geodesy, and then a commercial type application with an ROV pipeline survey. And right away, you can see that we've got two acronyms there, so don't be concerned if those aren't familiar to you yet. So a little more about my background. I'm a native of Massachusetts. I attended Worcester Polytech in Massachusetts, graduated with a mechanical engineering degree in 1986, and entered active duty in the U.S. Submarine Service, where I did 6 years as a nuclear engineer. But I was also a sonar officer and developed an interest in underwater acoustics and sonar, and I've made that the focus of my career since. After I left active duty in '92, I went to graduate school at the University of Rhode Island, got a master's degree in underwater acoustics and ocean engineering department. Worked for a year for a company called C-Beam Instruments that made multi-beam, full ocean depth bathymetric mapping sonars. And then 1995, I went to the Naval Undersea Warfare Center in Newport, Rhode Island, where I was responsible for undersea acoustic tracking systems for tracking submarines and torpedoes. I left there in 2003 to help start up a small business called Michael, and I was there until 2008 when I went to the University of Rhode Island Ocean Engineering Department as a research professor. And at that time, I formed DBV Technology primarily as a consulting business. And during my period at the Naval Undersea Warfare Center in 2001, I obtained a PhD in underwater acoustics in the Ocean Engineering Department with a focus on underwater acoustic positioning and joined the faculty as an adjunct professor. And down on the bottom here, you can see my reserve career. I stayed in the reserves for another, I guess, 19 years or so. Got retrained in diving and salvage. And I had duty assignments at Naval Sea Systems Command, supervisor of salvage and diving, mobile diving and salvage unit. And the last 7 years, I was at the Office of Naval Research and had some great exposure to undersea vehicles and the testing of those undersea vehicles. DBV Technology is my main focus right now. It's a small business. Our tagline is custom motion instrumentation. The common thread across the different instrumentation systems we develop is that they are almost all acoustic systems of some type. And the focus of those acoustic systems are navigation, positioning, command and control, communications. And we do a lot of rapid prototyping and a lot of testing in the ocean of these systems, from shallow water in Narragansett Bay to full ocean depth, 6,000 meters deep in or near some of the deepest trenches. So before we get into some of the technical discussion, I wanted to spend a few minutes going over terminology, and I apologize. Some of this may be known to people, but it may be unknown to others that are more commonly working in air or space domains. And so first, I wanted to go over the acronyms associated with the underwater vehicles. So we have UUVs, or unmanned underwater vehicles. Sometimes now they're called uncrewed underwater vehicles to make it gender neutral. And the UUVs have two broad categories. There's AUVs, autonomous underwater vehicles, and ROVs, or remotely operated underwater vehicles. And the main difference between them is an autonomous underwater vehicle, an AUV, makes decisions for control of the maneuvering of the vehicle, how fast to go, whether to turn left, turn right, what course to steer, what depth to maintain, is all done based on a computer, as opposed to providing those control signals to the control surfaces and the propulsion system, as opposed to a human operator in the loop providing those control inputs. An ROV, on the other hand, has a human that's driving the vehicle, steering the vehicle, and that is usually accomplished through the use of a tether, which is a wire of some type, copper or fiber optic, from the surface to the underwater vehicle. And so if we compare that to, say, a drone in the air, the reason we need to have that wire underwater is because we do not have the same advantage of radio links. Radio control or remote control cannot generally be done wirelessly underwater using underwater acoustics because there's not enough bandwidth and there's too much latency. So if you want to have a human controlling the underwater vehicle, you have this tether or wire or cable between the two. And so the remotely operated vehicle, the ROVs or the AUVs, depending upon the size, may require some type of LARS or launch and recovery system to get them in and out of the water from the deck of a ship. And for the larger, deeper ROVs that have these tethers, they'll have to have something called a tether management system, or TMS, because as you might imagine, if you're diving an ROV thousands of feet or thousands of meters down in the water, that's a lot of line in the water that has to be managed. And so there's these winches, tether management system, that controls the winding and unwinding of these very long tethers to allow operations at sea. On the navigation side, these systems, AUVs and ROVs, often have INS, or inertial navigation system, which has in it an IMU, an inertial measurement unit. AUVs almost always have some type of inertial navigation system installed. ROVs, on the other hand, may or may not have an inertial navigation system installed. And on the navigation and positioning system, there's the global positioning system, GPS, and then more generically, because other countries have developed satellite-based navigation systems, GNSS, or global navigation satellite systems. So GPS for the US, Baidu in China, Galileo with the European Space Agency, and GLONASS in Russia. On the right-hand side is terminology associated with underwater acoustic systems. And so for navigation purposes, there's a device called a DVL, or Doppler velocity log. We'll talk about that. The log is a nautical term that is a device for measuring speed of a vessel at sea. And it might be speed through the water, or it might be speed over ground. And a DVL, using a Doppler principle, is providing speed over ground, and it ties into the inertial navigation system, as we'll talk about. And then there's three terms here for acoustic positioning systems: LBL, or long baseline, short baseline, and ultra short baseline. And those are acoustic positioning techniques, or those are acoustic positioning systems and techniques that are used to get positions while underwater when GPS is not available, to allow an input to an inertial navigation system. And all of these positioning systems, whether they be long baseline, short baseline, or ultra short baseline, all have a transducer, a transceiver, and a transponder as part of their system configuration. So first, transducer, that is the physical device that converts electrical energy to sound, or sound to electrical energy. The in-air equivalent would be a microphone for converting sound pressure to electrical signal, or a loudspeaker for converting an electrical signal to sound. We do the same thing underwater. The equivalent of a microphone would be called a hydrophone, and the equivalent of a loudspeaker would be called a projector. But generally, we just refer to them as a transducer. And then there's two electronic devices, both of which have transducers as part of them, which is the transceiver and the transponder. And a transceiver and a transponder both have the capability of transmitting and receiving acoustic signals through the transducer. So why two terms? Well, the transceiver starts by transmitting and then receives, number one. Number two, a transceiver is usually initiating the downlink, or this transmission of the acoustic signal, waiting for a reply or receiving an acoustic signal, and then doing some processing on that to determine something like a position of the underwater vehicle, to allow that to be used in conjunction with the inertial navigation system. A transponder, on the other hand, listens first, receives, and then transmits in response to a signal that it has received from the transceiver. The other difference between the two is there's usually sometimes a one-to-one correspondence. You could have a system functioning where you have one transceiver and one transponder, or you might have one transceiver and multiple transponders. So for example, in long baseline, there's one transceiver interrogating or downlinking or transmitting to a set of transponders that will reply or uplink back to a transceiver. And then the last two terms is a pinger and a beacon. And I distinguish between the two in that a pinger is an acoustic device that goes underwater and it simply transmits an acoustic signal at some regular interval. And that transmission of the acoustic signal might be synchronous. It might be synchronized, say, to a GPS clock, or it might be asynchronous. And depending upon synchronous or asynchronous, that would have some effects on how you perform your underwater acoustic positioning, as we'll talk about. And then a beacon is a cross between a pinger and a transponder, where a beacon is a device that sits on the seafloor, is not constantly transmitting and only transmits when it's been interrogated by a transceiver. But instead of replying a single time, like is typically done from a transponder, it will transmit many times for some period of time and then shut off. So it's a transponder that can go into a pinger mode for a period of time. And by no means is this terminology black and white. Sometimes you'll see, a pinger might be referred to as a beacon. Um, so uh, that's pretty much it on terminology. Um, Maybe you've heard some of these terms before, maybe not. So with that, I'll go ahead and get into a few examples of these underwater vehicles. So here are examples of ROVs, remotely operated vehicles, that you can see that they come in greatly different sizes. The one in the upper left is the U.S. Navy Supervisor of Salvage and Diving underwater vehicle called Curve. And if you can see my mouse, that is an acoustic transducer right there. This is a deep diving ROV, thousands of meters deep, requires a tether management system, requires a LARS, a launch and recovery system. The upper right is a medium-sized work class remotely operated vehicle. If you can see my mouse, that is an acoustic transducer that's installed on that vehicle to provide acoustic positioning or communications to the vehicle. Both Curve and the work class ROV are shown without their tethers. In the lower right is a small commercially available, what's called inspection class ROV. And you can see an acoustic sensor here on the top. That's not used for positioning. That's actually an imaging sonar known as a forward-looking sonar that's installed on the vehicle. And almost always these ROVs are equipped with a camera so that the pilot topside that's maneuvering the vehicle has situational awareness around the vehicle. But of course, that's dependent upon the visibility and the environment in which the ROV is operating. And imaging sonars are very useful in those environments where you cannot see very well. For AUVs, we have some examples here, and they also run the wide range of sizes. We have a very small man-portable. This is a Remus 100 sized AUV. This is a Hugin AUV that can dive to several thousand meters. On the side of this AUV, you can see this black line. That is a sonar system. That's a side scan sonar system for producing acoustic imagery. And you can see back here, there's another acoustic transducer that forms part of the acoustic positioning and communication system. On the top right is an extra large UUV. You can see that this is of such a size that it probably will not be carried on board a ship and deployed. It would be launched from shore and sent out to sea to perform its mission. Generally speaking, on AUVs, as the vehicles get larger and they have more batteries, their operational endurance tends to be longer. And then the bottom of the screen are two unique type of autonomous underwater vehicles. These are called gliders. The one on the left, bottom left, is a sea glider, AUV, and the one on the bottom right is the Slocum glider, AUV. And what's different with these two as opposed to the three on the top is these gliders do not have a propeller. They do not move through the water using a conventional electric motor turning a propeller to get propulsion. Instead, a glider will start at the surface, become negatively buoyant, and change its ballast so that it's pitched downward. And then it sinks through the water column, but moves horizontally while it's moving vertically. So, for example, if it has a 2-to-1 glide slope, such as the Sea Glider AUV, which has a 1,000 meter depth rating, as it descends from the surface to 1,000 meters deep, it will move horizontally by 2,000 meters. When it gets to 1,000 meters deep, it will make itself positively buoyant. It will pitch upward and it'll rise through the water column and moving another 2,000 meters horizontally as it ascends 1,000 meters back to the surface. So through that dive cycle, it would generate 4,000 meters of horizontal motion. A similar principle is employed by the Slocum glider. Here's a few more examples of underwater vehicles. Top left is the US Navy's large diameter UUV. The top right is again the Sea Glider AUV. This particular Sea Glider is shown without the front end attached, and it's on a stand to do calibration of its inertial navigation system, but it's equipped with an acoustic transducer that you see here with my mouse. That is for navigation and positioning. The top has another transducer that carries a upward looking DVL, Doppler velocity log, and on the tail it has a magnetometer installed. And then on the bottom is another underwater vehicle called an EMAT. This is an expendable mobile acoustic training target. This is even smaller than this Remus 100 size vehicle here. These are used to allow training, simulate a submarine, and allow training when submarines are not available. So if we take a look inside a typical AUV from a navigation perspective, you'll see that there's several subsystems and components that are in there. You'll see that it has an IMU, inertial measurement unit, a pressure sensor to give it some indication of what its depth is, a DVL, Doppler velocity log, a compass, give it heading. That may be a magnetic compass. That may be some type of fiber optic gyro compass. And then you'll see these transponders here that can be used to obtain acoustic positions. These acoustic positions can be used to feed back into the inertial navigation system. And then to the right here, you'll see that there's sonar systems installed. You have imaging sonars and ranging sonars. You'll have the cameras. You might have a magnetometer. And then down in the bottom, you see this block for collaboration. And that collaboration includes working with other vehicles like a surface vessel to aid in the undersea operations of the autonomous undersea vehicle. In my terminology, I consider transponders and acoustic positioning systems to also be collaborative or cooperative, as opposed to other types of underwater acoustic positioning that might be performed in which it's uncooperative. You're just listening and trying to obtain the position of some underwater target. So in my terminology, I consider the use of transponders and transceivers in the various acoustic positioning modes to be a collaborative or cooperative means of acoustic positioning. So inside the AUV, and perhaps in some ROVs, you have your inertial measurement unit. The inertial measurement unit measures accelerations and angular rates and positions, so the 6 degree of freedom of the platform. And those can be used as an input to an inertial navigation system to attempt to keep track of the vehicle's position and speed and orientation as it's executing its maneuvers while underwater. And these types of devices, of course, are not restricted to undersea vehicles. They're used in other types of surface platforms, space platforms, aerial platforms. The IMU and the inertial navigation system, or the IMU as a key component of an inertial navigation system. And here we see an Exail inertial navigation system that's a fiber optic gyro based as some of the sensors in the inertial measurement unit. And to the right is an older Kierfought inertial navigation system. They come in different levels of accuracy, sizes, power consumption, etc., but a key component within the autonomous undersea vehicle. And I'd like to, I just realized I skipped over one thing on the terminology slide. I apologize. And that was down here at the bottom, positioning versus navigation. Two different terms. The relationship between them, navigation can be considered the science and art of maneuvering a vehicle safely from one location to an intended location. And so positioning is related to navigation in the sense that in order to navigate, I need to be able to know my present location. I need to know my intended destination location and be able to therefore calculate courses and speeds and maneuvers to navigate from one position to the other position. And on autonomous platforms, those are often stored in some type of mission profile that the onboard computer in the undersea vehicle will use in order to perform the navigation function. And so another key component within the overall AUV undersea navigation is this device called a DVL, or a Doppler velocity log. A Doppler velocity log is an active, what pulse echo type sonar system oriented downward, typically comprised of 4 transducers. So these 4 circles that you see here in both of these DVLs shown to the right are pointed towards the seabed. In this example on the left, this is attached to a surface vessel, but it just is, or it is attached on AUVs as well, or ROVs. And it will transmit 4 acoustic signals simultaneously down to the seabed. One of those acoustic signals is in a narrow beam pointed forward. One of the acoustic signals is in a narrow beam pointed aft, narrow beam pointed port, pointed starboard. It hits the seabed, reflects back, that reflected signal is received, and you measure the Doppler shift. And if you're moving forward, the forward beam would have an upward shift in the Doppler frequency, and the aft beam would have a downshift in frequency. And same thing for port and starboard. So you're able to determine your velocity over ground using this device. The reason this is important is because when an AUV leaves the surface, if it does not have a DVL giving it speed over ground, the error growth in the inertial navigation system grows unbounded. And whereas if you have the Doppler velocity log providing speed over ground as a reference, you can constrain that error growth. The problem is most Doppler velocity logs operate at a high frequency and therefore have a limited range, and therefore you cannot always have a lock or get the speed over ground measurements from the DVL at the surface with the AUV or mid-water column. If you're in 1,000 meters of water and the DVL can only function when you're 50 meters above the seabed, you have to descend 950 meters before your DVL can start giving you speed over ground. That creates a significant amount of error in the inertial navigation system. And that's usually corrected by using off-board cooperative acoustic positioning sensors like transponders and transceivers. So this is an example of an inertial navigation system that has been integrated with a DVL to provide this speed over ground as an input to the inertial navigation system to constrain the error growth. So now we'll talk a little bit about underwater acoustics in a sense of the limitations that are imposed by the undersea medium on acoustic signaling. And so there's this general trend, which is if you want to be able to use acoustics at longer ranges, you have to operate at lower frequencies, and at the longer ranges incur greater latencies. So typically a DVL, the ones that were shown here, they operate at a nominal frequency of say 500 kilohertz. Well, there you'll see that your range is going to be in the 10 to 100 meter range, and you will have to wait until an AUV has descended through the water column before a 500 kilohertz DVL is capable of producing speed over ground measurements. There are some lower frequency DVLs that exist that will give you longer ranges. The challenge there is that at the lower frequencies, your resolution and your accuracy of the Doppler shift and therefore your speed is reduced with the trade-off of obtaining the longer ranges. So shifting for a minute now to underwater acoustic positioning techniques, you have long baseline, short baseline, or super short baseline, which is also referred to as ultra short baseline. Excuse me one sec. Okay, I'm back. Sorry about that. So on the left here, we have the long baseline systems. In a long baseline system, you would have a transceiver attached to this. This shows an offshore floating platform for oil production or drilling. The transceiver is attached to that platform, and you want to determine its position. You would have multiple transponders on the seafloor, shown as T1 through T4. The transceiver would downlink an acoustic signal. Each of these transponders would reply back. The transceiver would then compute a position using a principle of multilateration. If it's, in this case, you would know the slant ranges directly because you initiate the downlink and get the uplink. And so it would be spherical multilateration. The positioning technique in the middle, short baseline systems, measure ranges and bearings to a single transponder and allow you to compute the position and heading of the vessel relative to a single transponder down on the bottom. And a super short baseline, you have a single acoustic transceiver receive array that transmits and receives to a single transponder on the bottom, and you measure range and azimuth and elevation angle, and you're able to obtain a position that way. Most of the systems in use presently are of the USBL or SSBL variety for providing the acoustic positioning to the undersea vehicles as an input to update the inertial navigation system. So now I'm going to talk briefly about 4 examples of underwater acoustic positioning and how these systems might work together, and then how it's tied into the other domains. And the first is undersea tracking ranges. So there's US and allied navies maintain various regions of the seafloor that are equipped with hydrophones placed down on the seabed and cabled back to a shore facility. And once those hydrophones are placed down on the seabed, a surface ship will transit relative to those hydrophones, transmitting an acoustic signal into the water synchronized with GPS. And so here we're tying together a space domain, air domain, undersea domain, and a shore domain by virtue of the fact that these are cabled back to shore in a lot of these permanently installed cabled undersea tracking ranges. After that's done, and after these hydrophone positions have been determined, then a submarine or a torpedo or an underwater vehicle that's equipped with a pinger can transit through this area, transmitting an acoustic signal. That acoustic signal is received at these hydrophones at known locations, detected by signal processing equipment on shore, and the positions of those underwater vehicles are obtained. And you're able to get positions constantly and hence track the undersea vehicles. Another application for the acoustic positioning and underwater vehicles would be conducting a deep seafloor survey. Why might you want to do this? Well, there's a lot of interest that has come and gone, and it's currently at the forefront now, which is deep ocean mining or deep sea mining or ocean minerals harvesting. And there's polymetallic nodules that are sitting on the seabed, and they're shown here to the right. Sometimes these are referred to as manganese nodules or polymetallic nodules because they have other important minerals in them besides just manganese. They have cobalt, nickel, other rare earth elements. So there's a lot of interest in mapping these and creating systems to go down and harvest these nodules. And before you're going to do that, you need to survey the area. And so you'll launch an AUV from the surface. That AUV now has to descend down to deep depths. So for example, in the Clarion-Clipperton zone, the CCZ, there's a high density of these nodules down there. And that's a water depth that's normally 4,500 meters, 5,000 meters deep. And so it takes several hours for an AUV to descend from the surface down to the bottom. It's incurring all that inertial navigation system error growth before it gets close enough for the DVL to get speed over ground and constrain the error growth. So in this type of a scenario, you would put transponders down, either several transponders and do long baseline acoustic positioning, or single transponders and do USBL acoustic positioning, but you would periodically get acoustic positions that you would feed into the AUV's inertial navigation system, so you get the level of accuracy needed for mapping this area prior to an exploitation phase where you start the harvesting operation. So in that deep seafloor survey, this shows that you could do it with one or more UUVs, and you could, instead of having transponders down on the seafloor, an alternative means of executing the survey and doing acoustic positioning would be to use a set of autonomous surface vehicles that would be transmitting acoustic signals to the undersea vehicles, allowing the undersea vehicles to have their positions, navigate, drive, and perform the mapping operation before they come to the surface. Another alternative method would be to use a towfish, which is somewhat between an ROV and an AUV. Typically, a towfish is like an ROV, but it doesn't have propulsion. The propulsion is given to the vehicle by the tow cable to the surface ship. And you drag this towfish over the area that you're interested in surveying. And you still need to know the position of the towfish so that you're capable of generating a map. Another application for the acoustic positioning is a scientific application called seafloor geodesy. And seafloor geodesy is the science of measuring the deformation of the seafloor at certain areas of interest. So this is an area off of Japan, and at this particular location, prior to the earthquake that generated the tsunami that caused all the devastation and the nuclear accident at Fukushima, there were a series of transponders that had been placed down on the seafloor. And in conjunction with GPS and acoustics, their location on the seafloor had been determined. After the earthquake, they went out with a ship with GPS and acoustics and positioned those transponders again. And you can see the net displacements that occurred of the seafloor on one side of the plate boundary as a result of that earthquake. And so there's an interest in extending this capability to not doing it with manned vessels, still using transponders on the seafloor. And the goal here is you put sensors down on the seafloor for long duration. You use an autonomous surface vehicle that transits, collecting GPS, transmitting acoustic signals into the water synchronized with GPS. That allows precise determination of the position of the seafloor sensors to centimeter level, sub-centimeter level position. And you can get those positions month after week after week, month after month, year after year through the use of a persistent autonomous surface platform. And the data from that surface platform from the seafloor is sent via satellite back to shore. And so here we're tying, again, these multiple domains together from the seafloor using underwater acoustics to the surface vessel, from the surface vessel through a satellite back to shore. And this is an area of active research right now that DBV Technology is involved in. If there's any further questions about it, you can reach out. And there's a couple recent articles that have been published about this work. And this is an example of some work with the actual sensors that was performed down off of Puerto Rico, right near the Puerto Rican Trench. This area up here is about 5,500 meters deep. This is about 3,500 meters deep. This is the autonomous surface vehicle. You can see the acoustic transducers mounted to the hull. And then these are the seafloor acoustic sensors, and you can't see the transducers. They're inside these white protective guards. And this is an example of some of the maneuvering that the unmanned surface vehicle would do, transmitting acoustic signals to measure slant ranges and allow us to do the precise positioning of those sensors on the seafloor, and bringing that data back to the surface acoustically and then relaying it via satellite to shore via SATCOM. And then the last example of acoustic positioning is something called inverted long baseline. And this would be an example of the use of acoustic positioning for conducting a pipeline survey. Let me see if I can play this here. And in this situation, instead of the pinger transmitting to sensors on the seafloor, they'll be transmitting to buoys carrying hydrophones, and those buoys are getting their GPS position. And then the underwater vehicle, such as an ROV, transmits an acoustic signal received on those hydrophones, detected and sent back to the surface platform that is controlling the ROV. And that is happening continuously. And by doing that, you're able to get a position of the ROV. And so you can see the camera here from the ROV as it's going along a pipeline, which is shown on the nautical chart on the right-hand side as the dashed line. And the real-time track of the ROV as it goes along is indicated by the yellow dots in the track. And so this is a system that has undergone operational testing out in California over the last year, and it's going to be launched as a new product in 2026. And with that, I think we should have some time to answer questions. I'll turn it back over to John.